Good day, good afternoon to everybody. This is my presentation. This is the first part of a two-part presentation. I will present the first part. My name is Antonio Lecuona, and the title is Photovoltaic Solar Cooking with PTC Ceramic Heaters Without Batteries. And I will perform as an introduction the theoretical presentation. Clean cooking offers alleviating the indoor smoke and deforestation. Electric cooking, named as e-cooking, offers advantages such as indoor cooking, and for that electric grid is not available in many locations, especially remote locations, or it is unreliable or too expensive. Moreover, it can include carbon emissions. Mini and microgrids offer great possibilities but require numerous users and large investment. So that individual photovoltaic cooking offers grid independence, indoor cooking, and electric supply for other applications. A photovoltaic cooker needs the solar panel that generates electricity, an electric dissipation to heat so that we can cook, a controller that usually is electronic, and storage for non-sunny periods and during the night. Commercial systems offer all of this, but including 1. Electronics, of difficult repair in remote and isolated locations, and batteries that are costly, of short duration, and polluting. So that a simple PV cooking system is necessary for the family and small community sizes. Let me explain you the two parts of our proposal. The first part is the solar panel. It is formed by a connection in series of illuminated diodes and some protection diodes. This is what you buy when you buy a panel. It shows an intensity that is proportional to irradiance, but there are internal losses when increasing the voltage and temperature. There is a reduction also. On the left part, you can see 5 different curves because they are for 5 different irradiance. It shows an intensity that is proportional to the irradiance, and it decreases slightly until there is an abrupt decrease reaching zero at the open circuit. On the right curve, what you see is again the 5 different curves. Actually, there is a continuous for the continuous variation of radiance, and we have multiplied the intensity times the voltage, so we get the electrical power. They are represented for the 5 curves as a dash curve, and you can see that there is a maximum power that we call MPP, maximum power point. So it is important to have a high efficiency to follow this MPP point, MPP tracking. Now let's go into detail about the resistance that is needed. For that, here you can see a figure where the intensity versus the voltage, as well as the power versus the voltage, is represented only for 2 curves, so that is more clear. One in brown color, it corresponds to a very high irradiance, the maximum typically available. And the black one is for 400 watts per square meter, that is what is available in the afternoon or in the morning. As you can see, the straight line is the resistance equation, and what happens is that the resistance needed to reach the MPP is smaller for a high irradiance than for low radiance. So that you can see that we need to change the resistance. Changing the resistance is approached in commercial system in 2 methods. One is using pulse width modulation, and the other one is using a voltage converter, using an MPPT, that is a maximum power point tracking, using in both cases electronics, and we don't want that for remote and isolated locations. This is the other part that we need in our proposal. is a resistance that is changing with temperature. This happens with some elements that are named PTC, positive temperature coefficient resistors. They are low cost and they are commercial. They are used in many places. What happens is that its resistance has two areas. One is at low temperature, medium temperature, and high temperature. What happens is that at low temperature, the resistance increases at above a temperature that is named the Curie temperature. The resistance grows very fast. So somehow we have a variable resistance that is good. There are two tools for making a solar cooker with PTC. One is installing several in parallel resistance and switching them for approaching the MPP. It depends on temperature. And the second thing is by an automatic limitation that is caused by the inbuilt Curie resistance increase at high temperature. So there is a limiting effect that is very interesting. On the left part, you can see a PTC and the direct connection that we are proposing in this communication. As a preliminary conclusion, connecting directly a PTC to a PV panel is suitable for making an electrical cooking system without any electronics or batteries. A detailed study must be performed in order to determine how to design this. There is still remaining the problem of storage. Without battery, we don't have electric energy storage, but thermal storage can be performed combining different ways. One is insulating externally the pot, so this way it continues cooking at low temperature. If this is not enough, we can put a phase change material such as erythritol that stores much more energy. And all these and other issues will be presented by Monsieur Jean Boubou in the second part of this presentation. You can find more info about these photovoltaic cookers in these communications made by myself. And as a last comment, after thanking your attention, please find here two books that I have written. One is about solar dryers and the other one is about solar cooking. You can get a PDF from them for free using this information that you can find here.